Uniform motion. We are calculating distance at 5 different points: 2 seconds, 4 seconds, 6 seconds, 8 seconds, and 10 seconds. From our video, we can see that our speed throughout is 7.0 kilometers per hour, which is equal to 1.94 meters per second. We can tell that this is 1.94 meters per second from 7.0 kilometers per hour from the simple conversion 7.0 kilometers per hour divided by 3.6 equals 1.94 meters per second. So this is our speed all throughout in these next 5 equations. So the first equation, we have time is equal to 2 seconds, and we are looking for our distance. Speed, 1.94 meters per second. Distance is equal to our speed times our time. So our distance is equal to 1.94 meters per second times 2.0 seconds. We can cross out the S's on both of these numbers because when we multiply them together, they cancel out. This leaves us with only meters for our distance, which is 3.88 meters. Due to significant figures, we have to round this to 3.9 meters. For t equals 4 seconds, distance equals speed times time. Distance is the unknown still. Speed still the same, 1.94 meters per second. So we do the same thing, except we multiply it by 4 instead of 2. 1.94 meters per second times 4.0 seconds. Again, we can cancel out the S's. This leaves us with 7.76 meters, which when we round it is equal to 7.8 meters. Same equation again, except we are using 6 seconds this time. Distance is equal to speed times time. Distance equals 1.94 meters per second times 6.0 seconds. Again, we can cross out our S's, and this will leave us with a distance of 11.64 meters, which we round to 12 meters. When time is equal to 8 seconds, with the same speed, 1.94 meters per second, we do the multiplication of 1.94 meters per second times 8.0 seconds, distance equaling speed times time. That gives us 15.52 meters, which when we round is 16 meters. And finally, at 10 seconds, speed 1.94, looking for distance. Distance still equals our speed times our time. Distance equals 1.94 meters per second times 10.0 seconds. Distance equals 1.94 meters. In all these scenarios, we cross out our S's, leaving us with a distance of just meters. When we round our 19.4, we get 19. So the distances that we find now can be used to make a position time graph for uniform motion. So, when doing accelerated motion to find distances, it's a different ball game from uniform motion. Uniform motion, you can just go distance equals speed times time. However, accelerated motion, you can't do that. D equals VT is a uniform motion thing only in physics. So, before we can find the distances, we need to find the average acceleration. We can do this if we can use our velocities at 0.0 seconds as V1 and 10.0 seconds as V2. Our velocities will be converted from kilometers per hour to meters per second by dividing by 3.6, like we did in uniform motion. I won't be showing it here, but it will be done. So our V1 equals 0.0 kilometers per hour north, which is equal to 0.0 meters per second north. Our V2 is equal to 16 kilometers per hour north, which is equal to 4.44 meters per second north. Our average acceleration is unknown, and our time we are using is 10.0 seconds. So V2 equals V1 plus our average acceleration times time is the equation we need to use to find our average acceleration. Now, we plug in our numbers that we're given. V2, 4.44 meters per second equals V1, 0.0 meters per second, plus our average acceleration times our time, which is 10.0 seconds. Where the V1 is equal to 0.0 meters per second, we can just get that out of here. We can take it out. We can cancel it out. It works out nicely. It doesn't change anything, so we're just going to get rid of it. So 4.44 meters per second is equal to the average acceleration times 10.0 seconds. Next thing we have to do to get the acceleration by itself is to divide by 10.0 seconds on both sides of the equation. This will leave us with our average acceleration equal to 0.444 meters per second squared. And when we round, due to sig figs, we are left with 0.44 meters per second squared for our average acceleration. From here on, we can go and do our distances for our position time graph, where again, we're going to look at the distances for 2 seconds, 4 seconds, 6 seconds, 8 seconds, and 10 seconds. So, our distance is unknown. Our time, we are using 2 seconds. V1, because we start from a stop, is 0.0 meters per second north, and our average acceleration is 0.44 meters per second squared. And please note at the bottom, for 0 and 2 seconds. For 0 to 2 seconds. That's very important. So our distance is equal to V1 times the time plus the half of acceleration times time squared, which is equal to 0.0 meters per second times 2.0 seconds plus half of 0.44 meters per second times 2.0 seconds squared. We only square the 2.0 seconds, remember. And again, we can get rid of the middle part of the equation because when you multiply 0.0 meters per second by 2.0 seconds, we're left with 0. So distance is equal to the second half of the equation, 1/2 times 0.44 times 2.0 squared. When we plug that into our calculator, we're given the distance of 0.88 meters, and we don't need to round because we already have two significant digits, and that's what it comes out to. So, therefore, our distance for 0 to 2 seconds is 0.88 meters. The rest of the equations for the accelerated motion distances. Now we're going to talk about 2 to 4 seconds. Every time we use a time of 2 seconds because we're using 2-second time periods, 2 to 4, or 6 to 8, or 8 to 10, or 0 to 2, 4 to 6. You get the idea. So, at this time, our V1 is equal to 1.111 meters per second north. Our time is 2, and then we use our same average acceleration for all of the equations, which is 0.44 meters per second squared. So our distance is equal to V1t plus half of AT squared. That gives us distance is equal to 1.111 meters per second times 2.0 seconds plus half of 0.44 meters per second times 2.0 seconds squared. And remember, only 2 is being squared. That means D equals 2.222 plus 0.88, which is equal to 3.102 meters, which we round with 2 sig figs to 3.1 meters. For 4 to 6 seconds, we use the V1 of 2.222 meters per second north. So distance equals V1 times time plus half of acceleration times time squared. So we plug it in to distance equals 2.222 meters per second times 2.0 seconds plus half of 0.44 meters per second squared times 2.0 seconds squared. This will give us a distance equal to 4.444 plus 0.88, which is equal to 5.325 meters. And when we round it, it's equal to 5.3 meters. Next one, 6 to 8 seconds. We use an initial velocity of 3.055 meters per second north. So when we plug it into our equation, distance equals V1 times time plus half of acceleration time squared, we get distance equal to 3.055 meters per second times 2.0 seconds plus half of 0.44 meters per second squared times 2.0 seconds squared. This gives us 6.11 plus 0.88, equal to distance, giving us a distance of 6.99 meters that we round to 7.0 meters for 6 to 8 seconds. This time, for 8 to 10 seconds, the V1 is equal to 3.8888 meters per second north. Our time still to acceleration staying the same throughout, 0.44 meters per second squared. Distance equals V1t plus half of acceleration time squared. Distance is equal to 3.8888 meters per second times 2.0 seconds plus half of acceleration, which is 0.44 meters per second squared, times 2.0 seconds squared, giving us a distance equal to 7.7776 plus 0.88, giving us a final distance of 8.6576 meters, which we round to 8.7 meters due to significant figures. The distances that we have now found, the 5 distances, can be used to make our precision time graph for accelerated motion